Hello, uh, this is Fahad, and in this lab we will discuss oil pumps. How do we do diagnosis, tune-up, and testing? Let's start. First of all, I would like to give you some information about pumps. So the first thing is, what is the difference between a pump and a circulator? Those terms are used interchangeably. However, from what we know, circulator do not do not have suction power. There's no suction in circulator. Pumps have the ability to provide a certain amount of suction. Like a sump pump, it can have more static head. So let's say static head is a main difference here. Okay, and so pumps can increase the pressure. This is the purpose of both circulators and pumps, is to increase the pressure and add some pressure to the water. There's a lot of engineering that goes into making a pump, and there's too much involved into the pump selection. But you have to know that there are two things you have to know about pump selection. One of them is the GPM, and the other one is head. By head we mean pressure, and by GPM is gallon per minute. The pressure of the pump, which is the head, is the velocity of the fluid inside of it squared times the area, that's the area of the pipe or the cross-sectional area of any opening where the fluid is supposed to go, and the density of the fluid. Another thing we have to always think about is the mass in will equal the mass out. So if we have three branches coming out of the pump, out, out, and out, the sum of those three will equal the inlet. So if this is 1, 2, 3, and 4, 1 will equal 2 plus 3 plus 4. Okay, so that's what we mean by the mass is always constant. Air bubbles are problematic for pumps. Pumps are designed to pump liquid, not air. If there's air, the pump might not work properly. Some pumps do not work in vacuum, meaning that they will not suck liquid if there's some bubbles in there. And also, if we look at a pump, so let's call this a pump here. There's an inlet, and outlet. So here we'll have positive pressure, and here we have negative pressure, and negative pressure is always called a vacuum. So pump priming, probably if you operated a pump in the past, like a water pump or something of that sort, probably you have to concern yourself with something called pump priming, meaning that we have to make sure that this part of the inlet has liquid in it. Otherwise, it might not be able to pull water or liquid inside if there is air. That's what we mean by pump priming. And sometimes in oil burners, we have to prime the line all the way from the tank to the pump, especially if the tank is below the pump. So that's something you have to think about. You might have the pump and there's oil coming to the pump, but there's no pump flow, oil flow, and that could be the reason the pump needs to be primed, meaning the inlet line has to be filled with oil. Moving on, this is an example of a pump impeller, not a circulator, and you can see how it is elaborately designed, where the liquid comes in here and pushed against the casing to create more positive pressure. So this is a circulator impeller. You see how it's different from the pump. It only pushes the liquid around, adding pressure, so it will be pushed around here, and eventually it will come out of this opening. So the impeller is completely designed differently than a pump. So a circulator just thrashes the water around to give it more pressure. Meanwhile, the impeller has the ability to pull the water or liquid inside, even against vacuum or air. So the parts, there's a motor that always attached to the pump to give it the turn, and usually the motor is connected through a coupling. So if this is my pump here, it's the exit and outlet, there's always a shaft here where you have a motor, and this is the coupling, the connection between the motor and the pump. So the pump and the motor, if you have guessed, they have to have the same RPM, which is the revolution per minute for the motor and the pump. And some pumps have a fan to cool them off. For big pumps, they require a fan to draw air in to cool the pump as it works. Not all pumps have that. And they also have a rotor and a stator, kind of like the motor. So this is the stator, and inside here is the rotor. The rotor is the one that turn around and push the liquid against the casing. So it's the same between the pump and motor analogy. So the motor, we have the stator, which does not move, and we have the impeller inside that move. I mean the propeller inside, or the rotor inside, that turns by electromagnetic forces, turns around, and the turning power goes through the shaft, and the shaft turns on this impeller in here, and that will push the water around. So it's good to know what are those little parts in the pump. For an oil pump, this is a typical oil pump, and some of them have more than one inlet and more than one outlet. So in here, if we look, this is my outlet that's going to the nozzle line. The nozzle line is very small, and probably this is my inlet, and there could be another inlet in here. So the reason we have more than one inlet, more than one outlet, is the flexibility. So based on how you want to align your pump, you can rotate the pump and have conveniently an inlet or an outlet where you want it to be. Also, you can connect two pumps in series or parallel as well, and also you can use the outlet to use one for the nozzle, another one you can put a gauge in it to indicate the pressure. So usually we have more than one outlet and one inlet. The pump pressure usually is between, for oil, residential oil, between 100 psi to 150 psi. Okay, so again, more outlet, and usually you find all the specification you need about this pump in here. So this will pump 3 gallons per hour at this revolution, which is 3,450 RPM. And again, between this, if we keep the pressure between 100 and 100 psi, if the pressure goes between 150 to 200 psi at the same RPM, you can have 2 gallons per minute. So if you notice, the amount of flow that's coming is decreased, even though we are the same RPM and have higher pressure. Why is that? That's because when we change the pressure, going back to the original equation, we have changed the orifice. So if pump pressure equal velocity square times area times density, and changing the area to give high pressure, so if the area goes down, the velocity will go up, and the pressure also will go up. So that's why we have less flow, and we know that flow rate, which is GPM, equal V times area. So if we decrease the area, we'll have less. If we decrease the area, we have less GPM. This part of the pump here is called the pressure adjustment, where you can go with a screwdriver, flat head screwdriver, and turn it clockwise to increase the pressure and decrease the area. So this little adjustment actually is changing the opening area to the outlets here. Okay, this here is the purging outlet, so we can connect the hose in here and loosen this screw a little bit counterclockwise. Don't take it all the way out because the pressure is really high, it will fly off. So just loosen it until you see some liquid coming from here, oil, and this is how you purge your pump. This is the pressure gauge that you will install in place of the nozzle line. So you take out the nozzle, where the nozzle goes, and you put your pump pressure to measure the output pressure. And usually it's between 100 and 150. And make sure it's very tight before you turn it on. What is tight? I mean the connection between the pump in here and this nozzle line is very tight, because the pressure coming out is at 100 psi, and that will splash if you have any kind of untight or unfit connection. So in the shop, I have this setup for you to try to diagnose a pump. So this is my inlet, oil inlet coming in, and you can see I connected some clear tubing so you can see the oil coming in. And this is my nozzle line. I took it out from the nozzle over here, and I put my pressure gauge so I can see the pressure. And what we do is we turn it on, we bleed the line by loosening this nut over here, then you tighten it back again. So you loosen the nut, you see the oil coming up, and you see some bubbles coming out, and you turn it off again, and you will see the pressure here turns up to 150 or 100, and you can adjust from this point over here. And to know if the pump is not faulty or it's not leaking, you can turn off the power, and the pressure here should drop by 15%, no more, and stays there. So the pressure will be, for example, here at 100 when it's on. We turn it off, it should be at 85, which is 15%, and stays there and does not drop. If it keeps dropping, that means something is wrong with the system and there's a leak in the system. Okay, so things we want to check: we want to check for leaks, make sure it's not leaking, so it's a good way to clean it, and look for small little leaks. Check for bubbles. When you bleed the line, you want to make sure there are no bubbles and there's solid flow of oil. And this process called purging is when you take the oil out and let out all the bubbles. Check for pressure, adjust the pressure, and check for pressure stability. If we have a pulsating pressure, so if we turn it on, the pressure goes back and forth or vibrates, something is up with the pump, and probably the impeller is not working very well, or probably the motor is weak, so you have to check for that. Noise, what kind of noise we are checking? We're checking for vibration, excess vibration. Also grinding or rattle. If it rattles, it means something is loose inside, it has some dirt or broken parts. We can also check for vacuum. There's gauges that can connect both to the outlet and inlet, and you can turn on the pump and it will show you the vacuum. There's a video by Sid Harvey, gauge manifold, that explains very thoroughly how do you check for vacuum and for output. So there's another video by the gray furnace guy that is also posted on Blackboard. You can check for adjustment of the pump and some of the common problems you'll face in the pump.